para trás. Faça dismiss. Não. Posso? Se fizer aqui. There we go.
Obrigada.
Yeah. Okay. So before I start, I'm just going to give some context and a quick intro to MemSQL. This is a rough sketch of what a MemSQL cluster looks like. I'm not going to go into all of this. We're going to explore a very small part of that, specifically replication. But to motivate why we need it, basically, we have a database here, and that database is sharded into multiple partitions, and each partition has redundancy. And we do that so that we can provide durability and availability to our partitions so that if there are failures, you don't lose your data, your transactions don't go away. And today, I'm going to talk about redundancy and replication within a single shard. So a quick intro, I'm going to talk about transactions. Transactions are what your application uses to talk with a database. So if you build an application, what it's doing is it's sending read transactions to the database to see what the state is, and also updates or writes or deletes to make modifications to that state. And you want a bunch of very nice properties from transactions so that writing applications is easy. The one we care about today is that transactions are durable. What that means is that when the system tells you your transaction has committed, if you wrote something to the database or if you made a change to the state, that change is not magically going to go away because something failed. And the way you maintain durability is in doing two things in most systems. The first thing most systems do is they have a transaction log. What the transaction log allows you to do is persist to disk the binary format of your transactions. So you can imagine that you're making changes to the database. You say, write the number 10 on my database. And the way it goes about doing this is it first will persist that to disk before telling you that it's committed or necessarily even making those changes visible. And when the disk tells you that the number 10 is going to be committed, you tell the user that it's committed. This is an oversimplification. And a lot of this presentation is going to have oversimplifications because replication, transactions, and durability is a fairly hard topic. I'll try to note what oversimplifications I use so that if you have any questions during the coffee break, I am very happy to talk about it. But basically, transaction logging is what you use so that if you crash, when you restart, you have a log of your transactions, and the user never hears that a transaction is committed before it's persisted to the log. Some systems actually write the how to undo the transaction first. MemSQL has one simplifying factor, which is all the mutable state actually exists in memory, so you never need to undo anything. Systems that write to disk need to undo the changes because they might crash in the middle of doing them. But in memory, we just lose everything, and we just replay the redo log. So it's just how to apply them. The other way we maintain durability is with replication. This doesn't give you just durability. This also gives you availability. The idea is that you never really want your data to live only on one machine. You want it to live on multiple machines because you might lose one machine, and even if it's temporary, then your system is completely offline. So if it lives on some other machine, you can make it the new go-to machine for this piece of data. Also, you might lose one machine forever. Imagine that, I don't know, one of the racks in your data center suddenly went into a volcano of its own will, and now it's not coming back. But at least you always have another machine that has it, hopefully on another rack, that has all your data, and you just keep going. The type of replication I'm going to be talking about today is primary-secondary. There are others, consensus being the second most popular out there, or I don't know if it's the most popular now, but one of the other popular ones. And the idea with primary-secondary replication is that there's one node that is the primary, and that's what the user interacts with. It doesn't necessarily interact with the primary directly. An example is in the MemSQL cluster, we have an indirection layer because the data is sharded. So we have one node that's responsible to know where things go. But for this presentation, you can assume that it's the user interacting directly. In MemSQL, those would be the nodes we call aggregators, but they are kind of users of this copy. And then the primary node sends over the network to the other node the transaction log. There are other kinds of replications. You can do statement replication, where you're sending the statements the user sends you, which is still kind of a transaction log, but we use physical replication and physical durability, which means that we actually persist all the effects of a transaction onto disk. And that allows us to actually do some more interesting things, because with statements, the order of the statements matters a lot. Whereas with transaction changes, the order doesn't necessarily matter as much. So you just persist all the effects. And we just send over the network such that the secondary always has a logically equivalent copy. So I've been working on this for longer than I care to admit, or anyone else should know outside of MemSQL. But we just shipped a revamped replication system in MemSQL 7. I'm not going to describe everything we've done. There's like 50,000 lines of code there. There's not enough time in this day to describe everything that goes into it. But I will go through how you would build a replication system of your own. And I'm also going to go into some detail into one of the optimizations we made to make our new replication system very fast. Again, be warned, there's going to be a lot of oversimplification. I'm going to gloss over things like failures. I'm pretty sure about 2/3 of those lines are failure handling so that things don't blow up. But let's go into it. Building your own replication. So first, we should define what the goals are. What are the objectives? We have a primary and secondary as before, 2 nodes, and we want the secondary to be a logically equivalent copy of the primary. That just means that if I point my workload at the secondary, I should get the same responses as I would on the primary. What is highly desirable is that it is performant. You don't want replication to be taking a very long time out of your system. And you don't really want to underutilize any resources. So it goes hand in hand with performance. Like at some point, you're going to be bottlenecked on the pipe of the network or the pipe to disk, whichever one is smaller. And if you are underutilizing those pipes, that means you leave performance on the table. And you can just get more. So how would one go about doing this? Here's what a naive solution would look like. Now, the idea is when your transaction finishes, before you make its effects visible, and this is somewhat based on what MemSQL does, so it's not necessarily the only way to do this, but it is kind of a useful abstraction of how one would go about doing it. So you figure out how you're going to serialize your transaction, like the binary format. You write it to disk, you send it to secondaries, and you declare it committed. And on the secondary, you're just receiving from the primary, also persisting it to disk, because you should have your transaction log there, and then applying it on the secondary as well. Does anyone know what is wrong with this?
You didn't wait for the secondary to get back.
Exactly. So does anyone know why that is a problem?
Sorry?
So the answer was you didn't wait for the secondary to get back to you. So it might not be completely obvious because you might think that the sends are blocking, but most systems would not do that. They would just say, I'm going to send and forget, right? It's completely asynchronous. But there, we're not waiting for the secondary to tell us it's received the transaction. What could go wrong with that?
Because then if your first one dies, you have like corrupted data.
Yep. So this helpful diagram I drew in my notebook earlier shows that. So like the user sends a transaction, the primary sends it to the secondary, but it just kind of gets lost halfway. The primary says, OK, transaction has committed to the user, and then it goes offline. We promote the secondary to primary so that the workload can keep going. The user asks about its transaction, and the secondary just says, I don't know, never happened. All right, so the way we fix it is we wait for acknowledgements. the secondary also has to send it back. Now, what is wrong with this one? This one is a little subtler.
What is commit?
Hmm?
This is a typical two-phase commit approach.
Right. Yeah, this is typical two-phase commit, but there is still something incorrect here.
You have a problem with waiting for latency.
So that is a great point. We can wait forever on here. For this presentation, we're not going to fix that. What you could do is the secondary doesn't necessarily, so we care that there is a secondary that's eligible for promotion that has all the data. But if there's a failure in the secondary, you're never going to get an ACK because it's gone.
Can't you just get an ACK after the transaction log is stored?
Well, but it's stored in one place. You want it to be stored in two places, right? So
you could like go from the transaction log and store it into disk, even if it fails.
well, the log is on disk still, but we're saying we want it on some different machine, right? Because if your primary machine fails, you don't want the workload to die, or you don't want to lose data if your primary machine fails forever. What you could do for this is you can have some other system that notices the failure in the secondary and in a way demotes it from being a promotable secondary. And that way you don't need to wait for ACKs from that secondary anymore. You would lose one copy of the data, but the same system can try to guarantee there is a new copy before it allows that to happen. I'm always talking about a single secondary here, but you could also have multiple copies already. You don't necessarily just have to have one other copy. And in a way that allows you to stay available. If you just have something detecting the failure, saying, I don't care about this secondary anymore, I have a copy somewhere else, let's keep going. What else is wrong with this?
It looks slow. Can't we send ACK right after sending to disk?
That's a good observation. Before sending to disk, we can't, because then if the secondary dies right there, your data is gone. We could do it right after sending to disk if all you care about is that the data is persisted but not necessarily visible. And in this case, we kind of care, but that means when you promote the secondary, you have to add an extra step waiting for the data to become visible so that you can use it. Otherwise, you would get the same kind of problem. But at that point, the data is persisted, so it will eventually become visible.
Can't you send to the secondaries first? That's strange.
There's nothing that stops you from doing that.
That's strange, because then you can have a transaction on the other side and then the first one fails.
But it's equivalent to having the transaction on the first one and then the other one failing, right? You could do that. You could also just pretend the disk is one of your secondaries and basically pretend it's like a special machine, and now you're just treated the same way you would treat all other secondaries. That's actually a very useful, simplifying way for coding it, because then you don't have to replicate a lot of the logic. But disks are special. That's one of the things I'm going to oversimplify here. We're not going into how disks are special, because it's awful. Like, they tell you they've persisted their data, they haven't. They tell you they've persisted their data, you write something to them, they overwrite your data. You have to be very careful when dealing with disks. There's something else wrong here. Or there's something, it's wrong because it makes things very, very hard to code, but it's weird. So imagine that you have many concurrent transactions running at the same time. How could that break things?
Does the transactions can read from the secondary?
No,
or they all are always processed by the primary?
Let's assume they're always processed by the primary. So if you have multiple transactions going at the same time, they can reorder when they send to disk and when they send to the secondaries.
Because if the first line takes too much, then
Yep.
you write it in disk. Okay.
So you always have the guarantee that the secondary has all the data, but the transaction log is not necessarily the same. This is not necessarily incorrect, right? Because the main goal we stated is that they are logically equivalent, and these two are logically equivalent. They have the same set of transactions in their transaction logs. But things become really tricky if you need to catch up a secondary. So imagine that the primary fails, and you fail over to a secondary, and maybe there's another secondary, and now this secondary also fails. And now you have 3 different transaction logs. This secondary comes back up. And at this point, you don't necessarily want to send everything to it from scratch, because that could take a long time. The failures could be temporary if your restarts are quick, or it could be a network issue that caused you to detect a failure, whereas the node was still online, and maybe it just lasted a second. And now, if you have a lot of data, it could take maybe an hour or more to provision this secondary from scratch. But you know that this secondary at some point was synchronized with you. It had the same transactions. You just want to send the missing transactions. And now, the transaction logs are different though, so you don't necessarily know what it's missing compared to you. If the transaction logs were the same, then you know that there is an offset at which, before which everything is the same. That offset is actually not too complicated to compute when things are the same, because you know that if something is committed, so if you've got an axe for that transaction, then everything before that transaction is the same on every node, if the transaction logs are the same. And you can basically send that offset from the primary to the secondary saying, okay, everything before this has been committed. And you can either do it periodically, and in MemSQL we just do it kind of lazily when we need to write something new, we just send that value if it's changed. And so you can use that value as the offset if everything is the same. If everything is not the same, then you may have missing different set of transactions before that offset on both, or that offset just doesn't make sense anymore. So how would we go about fixing this?
Can you just send like the last version of the transaction log from the first one to the second one? The second just grabs that and applies it?
Not sure I follow.
Okay. Imagine, so you said you have the transaction happening on one,
Mm-hmm.
and you send that transaction together with the data
Mm-hmm.
to the second one. And
Yeah.
the second one grabs that data and persists both the transaction and the data itself.
Right, but so the
What if you send the log already computed, the transaction log already computed, the second one just... So you always send like a valid copy of the transaction log.
oh, so I guess is the idea that you always send, instead of sending when a transaction commits, you just send the log as you write to it. So you could do that. That becomes very slow.
Okay.
Because you basically have to wait for the log to be written up to where you wrote to it. And that's not necessarily going to be fast. You can imagine you have a transaction that's going to take an hour to write to the log, and then another transaction that's going to write to the log next. And that's going to be a bit slow. In a way, it's a reasonable solution. It's sort of what this is doing. Basically put a lock in there so that you send to disk and to secondaries at the same time. And you're just going to send as you write to the log. The difference is the transactions can write to disk in that solution all at the same time, and then only later does it send to the secondaries. But you still have to wait for that to happen. So I kind of spoiled it. One of the big issues here is that it's going to be pretty slow. I drew a fun graphic here. So you can imagine you have a bunch of transactions all doing work, all doing progress at the same time, and then they're all going to compete on the same lock. And this is not necessarily the exact way it's going to happen, but you can imagine that if you read it just like here, you're going to send to disk first and then send to the secondaries. So while you're waiting on the network, your disk is empty or it's not doing anything. while you're waiting on disk, the network is not doing anything. You could do these in parallel, so you could like push this back, but there's always going to be one that's slower, either disk or network. And while one is executing, the other one is waiting for it, right? That can be a pretty big performance bottleneck. And that was actually something that could sort of happen on older MemSQL versions. And what we did, so can anyone tell me what they would do to fix this, to avoid this bottleneck?
Generate like sequence number. Since it's the primary that processes all the transactions,
Mm-hmm.
and generate the sequence number for each one. Then send without locking to the secondaries, and the secondaries need to always know what was the last one that they wrote, and check if what they receive is the next one, or if they should wait for, if they are receiving, like the last one was 1, they received 3, so they know that 2 should be, should arrive.
So basically moving the lock to the second. It's the same, same performance,
Well,
not quite the same
depends
performance.
in the way it writes on the log.
So the suggested idea is each transaction has a sequence number, and you write them in that order to the log. But you have to do it locally as well, which can also become a bottleneck. And then on the other, but you don't need to lock around the sending over the network. And the secondary just has to make sure that it writes them in the same order. That has the problem that they would still kind of lock on the disk, right?
Yeah.
So you'd still be all waiting for disk before each transaction has to wait on every other transaction to write to disk before it can send. So I think it still isn't ideal, but it's close. It's very close.
What about the mix between that and also using a random generator number? So something like sequence with 3 actions then in that. You just send like a random generator an ID, like an order.
Mm-hmm.
You just send the 1, the 3, and 2. But you know already that they are representing the same transaction, but they have an order that doesn't matter. You just get the order correctly at the end on the second node.
I'm not sure I follow. Wouldn't that have the, so the idea is to add a random number generator.
To represent the transaction. So
Okay, so each transaction has a unique ID, basically.
Yes. But the transaction also could be represented by, let's say, a free action, like a write.
Right.
Okay? So you don't have to wait on a disk, you just persist them with the same random generator, but an order can be 3, 1, 2, for instance. But when you're collecting the information from transaction log, reading in the correct order. So the persist on the disk should be.
So you persist it out of order, but then you reorder them at the end?
Yeah.
But that has the same issue as before, right? Where you don't necessarily know how to, you don't necessarily have an offset to send things after. Right? The problem from before was that computing where to start catching up a new secondary is very hard if things are ordered differently on different nodes. I think that would still have the same problem.
Is the solution like sacrificing the secondary startup time?
No, you shouldn't have to sacrifice the startup time. Right. I'm going to count to 5, see if anyone has any other ideas. One.
You can afford to have some rollback when you have conflicts, and if you have at least one piece that provides you the commits to have some kind of eventual consistency on top of that, you can have different groups of primary backups, and you can at least attenuate or diminish a little bit that log. It won't prevent it, but you'll at least reduce it. So different groups of primary backups according to your workload.
Well,
doing some kind of sharding help.
You could do sharding, and it does help because now you have some parallelism for different locks, but we still want it to be faster per shard. So MemSQL does do sharding, and there was some debates we had over, is it a good idea to make replication much faster because you still have parallelism across shards. And we found that it was still a very good idea to do it, to make it really fast. All right, 1, 2, 3, 4, 5. Okay, so it's very similar to the sequence number idea suggested initially. So this is one of the optimizations we implemented in Repilog. There are a few others, but this is the one I'm going to go into more detail in here, where you still allow sending to the secondaries out of order, but you don't just send the transaction content. You also send the offset in the log where it's written. And the way we do that, so you have to be very careful when you do that, because you can't just write on the disk. Otherwise, if you have two concurrent writes, they might just write on the same offset. What we do is we have a counter for each shard that says where we're at on the disk. And every time we want to write a new transaction to the log, we increment that counter by the size of the transaction. And the current value of the counter gives us the current offset. And you can do the increment in an atomic manner without using locks. And the hardware is sort of using locks, but it's pretty fast. And then you have your offset. And then you just have to, you know that no other thread, no other transaction is going to touch your reserved portion of the disk. And so you write to disk, there are no locks there. The socket still sort of has a lock. It doesn't even need to be an explicit lock. Like when you call send on a socket, it will go to the OS, and the OS will just send everything serially. But at that point, you just send the offset and the transaction log content, and you're able to effectively max out the network pipe, at least. And
don't you then have like empty disk space at this portion if you reserve the offset, but then it fails?
That is a great observation. Yes, so one of the great challenges of doing something like this is that if something fails, you have portions of the disk that are empty. And now you have to be able to distinguish those from non-empty portions. And you also have to deal with those when trying to figure out where to send, where to do the catch-up. So when you're doing, for the catch-up part, it's not actually very hard. We do basically the same thing as before, because we have something in the background in our replication system that knows an underestimate of everything below this offset is already committed. And so you know that everything below that offset doesn't have any gaps. And so it is safe to use that offset for to start catching up. Above that offset, the challenging part is suppose that your primary fails, right? And you have a secondary that has a hole. You have to know how to identify that hole. And what we do, there's actually a lot more that we do that's not here, but we basically have a checksum for each transaction block that allows us to distinguish between something that was written, so we just read the entire log and check against the checksum, and something that's a hole, or we call it torn pages. And that allows you to kind of skip it, and we can basically overwrite other secondaries logs with that hole, and they know to skip it as well if they need to recover.
So
yeah.
A lot here. If you're applying the log right after writing the log to this, if you have a gap, you're basically applying the transaction in the wrong order.
Not necessarily. That's actually a great question.
Unless they are commutative.
Right. So they will be, so the question is, if you have a gap and you're applying right when, if you're just replicating out of order and you're applying right when you receive the data, you might be applying things out of order. And that is true. You're not applying things in the same order as in your primary, necessarily, but they are going to necessarily be commutative, because you can have dependencies on a transaction that is going to commit by another transaction, right? If you have a hole, that means that everything in that hole or that gap is not committed yet necessarily, because you haven't acknowledged it. So if you're going to apply something after the gap that you've already received, that means that the two transactions are running concurrently and are committing at the same time. And if that is true, then they will not conflict because they both validated their commits at the same time.
Oh, when you reach
yeah.
this point, you already validated.
Yeah. So
they are committed.
yeah. So in memSQL, we actually use pessimistic concurrency control, which means that they just have locks on everything they're going to write, which is how we can guarantee at that point they're not going to conflict. You could have other mechanisms with optimistic concurrency control where you just scan your write set. If we did that at that point, we would already have validated.
So to mention, what is the isolation level provided by memSQL?
So today, it is pretty bad. It's read committed. Read committed isolation level is actually just guarantees that you'll never read data that was never committed. So, but it's pretty weak because you might read data in the middle, like you might read something in the middle of two transactions, for example. You might see half a transaction, half another. That's actually what I'm going to be working on at memSQL for the next few months, increasing the isolation levels we support. So pretty exciting stuff. The main reason we don't have higher isolation levels right now is that it is due to the distributed nature of the system. Everything is sharded. We don't have a way to tell between two shards of the data that two rows were committed in the same transaction right now. And so within one shard, we actually do support higher isolation levels. You can do snapshot reads, which guarantees you that you don't ever see half a transaction. And it's fairly easy to build on top of that for snapshot isolation or even read committed when performance. But we are working on for the next major release of memSQL in a few months to have higher isolation levels, hopefully. We're all engineers here. We all know how planning can go. How am I doing on time?
Good.
Okay. So does anyone have questions about this?
The only kind of weird question I have is, it feels weird to not write to disk continuously. I'm not sure if that's actually a problem.
When you say continuously, you mean like always appending, right?
Always appending. It's weird to go back in offsets when writing to disk.
It isn't. It may feel weird, but it's actually not a problem. Because what you do, you kind of still write continuously when you reserve here. So one way to think about it is when you're writing to a file, you're actually doing, if you're appending at the end, you're actually doing two operations. You are moving the size up, so there's a metadata change on the file system, and you're also writing all the pages to disk. And what we're doing is kind of moving the size change into the transaction. So these two operations together are sort of equivalent to writing at the end of a file in the file system, because it's still two operations. That's actually a tricky thing, because if you're doing synchronous writes to a file, and your file is not a fixed size, and you're moving the size up, your writes might go through and tell you they're persisted, but the metadata change could be independent. And so you have to either pay a very high cost to make sure that the metadata change goes through and is persisted, or you can pre-size files, which is what we do. But that has the separate cost that now you have to keep track of the end of your log separately and manage that yourself. So you still need that metadata somewhere. We just thought we could do better. I think we do better. Any other questions? Right? That is it for the presentation. We are hiring in Lisbon. If anyone's interested in working on interesting problems like this one, we also have other teams that work on different types of problems, and like front-end, back-end, systems management. And if you have any questions about this presentation, the work we do, or if you're interested, we have a bunch of people from memSQL here right now and later. Thank you.
Okay, thank you, Rodrigo.